Thank you. So I'll continue the Rydberg story, which is something that my group has worked on for quite some time now. But this is my first molecule conference, so I've really enjoyed like interacting with everyone here, and so learning more about conventional molecules. And I hope I can tell you something about like these very unconventional molecules, following a bit Matt's introduction here. But I'll be talking about a different kind of Rydberg molecule. Okay, so the work that I'll be showing you is theory work in collaboration with Immanuel Bloch's group, and all the data that I'll be displaying was really taken by Simon Hollerith during his time as a PhD student in Immanuel's group. All right, so if we consider a very simple system, like a two-level atom, coupled to some sort of continuum, it has the opportunity to decay, right? And that decay, whoops, that's the wrong direction. And so that decay is determined by the coupling strength of that two-level system to the continuum and by the density of resonance states. So the larger the coupling and the larger the density of states, the faster that decay happens. And so we know that from like systems like water here. If you excite water from the ground state to the excited state, you can couple it, so to say, to an ionizing state and thereby photodissociate the water molecule. And so in a pictorial picture, you have an isolated quantum state, some sort of coupling that could be laser mediated or just vacuum fluctuations, and it couples to some sort of continuum of motional states, and that's decay. And typically in normal conventional molecules, the vibrational frequency is in the tens to hundreds of terahertz range, and the dissociation rate, of course, depends on the laser frequency or on the laser power, but is much lower, and so that's a perturbative process. And I will be telling you about an example system where, you know, coupling an isolated quantum system more strongly to the continuum can lead to a situation where that decay is actually reduced and can even be switched off entirely. Okay, and I will preface this by saying that there are other exceptions to the rule. So, for example, in ordered arrays of atoms, the decay rate also does not only depend on the two like ingredients that I told you about, but it does depend on the geometry and can be significantly modified. The same applies to low-dimensional semiconductors, where collective light scattering changes decay rates. And of course, there are also bound states in the continuum in like more complicated systems here, where basically the interference of different channels leads to like these resonant states, resonances. Okay, so Rydbergs, I don't have to say very much about it about them after Matt's introduction, but basically for everyone who hasn't worked on Rydbergs before, they really scale quite massively with the principal quantum number, and that applies to the size, the line width, the binding energies, and the interactions. So think about Rydbergs as like, you know, exaggerated atoms in every sense, and they also produce exaggerated molecules. So in a nutshell, what I'll be talking about are like these potential energy curves that, for reasons that Matt explained, don't really cross, and you form, you know, normal molecules. The point here is that for Rydbergs, and now we have two Rydberg atoms, not as in Matt's case, one Rydberg atom and a ground state atom. So two Rydbergs, and the vibrational bound states they form now have bond lengths in the, you know, hundreds of nanometer to a micron range. So you have these giant dimer molecules. All right, so here's just a, like, you know, a little picture comparison between these macrodimers, and you see there in every sense they're totally extreme molecules with very low vibrational energies compared to, you know, conventional molecules that we've otherwise heard about. All right, so we can calculate them, and those are the calculations. I won't spend much time on that. And then experimentally, you see lots and lots of vibrational states. All of, like, every one of those corresponds to one of the vibrational states, which we call a macrodimer, like these Rydberg macrodimers. Okay, and then they're measured by putting atoms on a lattice, illuminating them, and every pair loss is then associated with the creation of a macrodimer, and that produces the spectroscopy that I showed you on the last slide. So going forward. Okay, so the excitation scheme proceeds from atoms in the ground state via an intermediate singly excited state to this molecule. And I want you to focus your attention really to this upper level. So if you have a macrodimer, switch on the laser, you couple it to the dissociated state of a singly excited Rydberg atom and the ground state, and that is a resonant coupling and falls just into this paradigm that I introduced in the beginning, isolated quantum state coupled to a continuum, right? So that's what we have. And if you want to model that, that just is a Fano model, a little generalized isolated state, the continuum modes, and the coupling. The coupling now can be enhanced by increasing the laser power. And so what's special now is that for the Rydberg molecule, the vibrational energy scale falls in the megahertz regime, and so does the coupling. And that makes it very different from conventional molecules where those energy scales are totally separated. All right, so we want to predict how the single macrodimer resonance, shown on the left, is changed if you increase the laser coupling. So you move into the strong coupling regime. Okay, and here's the result, basically just obtained from calculation. Okay, I will not use this laser pointer. And you see that the single line really splits into three, and we find a lower resonance, a higher resonance, and a central resonance. And they are split, as you might imagine, by the laser or the coupling laser amplitude. And so now in the calculations, we can look at the vibrational states that are associated with each of those resonances. And we find that both on the lower and on the upper side, we find actually a vibrational wave packet that corresponds to that of the macrodimer. So it's really like tightly bound state. And in the middle, we have like some, vibrational state that basically consists mostly of the trap states. So it's very wide. And on the sides, we have these resonances. And as you increase this coupling, you see that these peaks become more separated, and they also become narrower. And in fact, you can show that they become stable in the large coupling limit. So in fact, it's the upper resonance that becomes more and more stable as you increase the Rabi coupling, while the lower one is already stable or at very low couplings because it shifts out of that continuum. So in some sense, we create new states where the decay of that macrodimer is switched off, and instead we have these stable states that we call the negative macrodimeron and the positive macrodimeron. Okay, so you can also look at that in quantum scattering theory. I will skip that part in the interest of time. If anyone's interested, we can talk about it later. But the same results could then also be seen experimentally. So here we see the spectrum. As the coupling laser is increased, we see that these peaks move out and get narrower. Okay, so if that happens for two atoms, there's the possibility that if I have a bunch of atoms on a line, like shown here, that I might have a macrodimer on this link or on this link, and there might be a light-mediated link between the two. And that's what I will explain now. And that really connects very nicely, or is an example of these field-linked states that we heard about a couple of days ago. Okay, so repeating the calculation for three atoms, we find a spectrum that's very similar. And indeed, like if you look at these resonances now, this is in relative coordinates between atoms 1 and 2 or 2 and 3. They're quenched in either one of the coordinates. And that's really analogous to the calculation that I showed you before. And so is this middle peak that is also analogous to what we've seen before. But there is this nice little peak on the far left, which actually corresponds to a state where the molecule, where three atoms are now bound into a molecular state, although the molecular interactions really are only binary. So that's what I would call, or that's what we did call a macrotrimeron, but I think it's an example of one of those field-linked states that we learned about. Okay, unfortunately, the experimental resolution in the spectroscopy isn't quite good enough to resolve that peak, but by looking at loss correlation, so a more microscopic approach, there are actually signatures of that positive correlation, so of really molecules of more than 2 particles appearing, and there's indication that this can be extended to even larger molecules. Okay, so now I want to use the maybe last 2 minutes to give you a little preview on ongoing work that we're doing in collaboration with Dia Vagese, like who has visited my group or visited my group last year for about a year, and her advisor in India, Rajesh Nath. So we're looking at interactions between pairs of macrodimers. So we want to go from the single macrodimer limit to multiple macrodimers. And those are, of course, 4 Rydberg atoms, and that's a relatively complicated computation to figure out like how these 2 macrodimers interact. Won't go into the details, but I'll just show you the results. So if we, so here shown for relatively large separations, we see this emergent kind of dipolar-like looking potential that is repulsive on like the head-to-tail axis and attractive in the other direction. And so here is a cross-section of that going once around the circle. You see this transition from repulsive to attractive interactions. Okay, so I'm running out of time, but I would like to mention that there's actually, in this vein of like talking about molecules are the new atoms, we make this comparison between Rydberg stat calculations for atoms, which just have a few first-order channels that are relevant to compute the Rydberg-Rydberg interaction. And then if you look at molecules, now suddenly there's an entire forest of first-order states that, or first-order channels that matter. Okay, now we can apply this to blockade. This is our, very preliminary prediction of the blockade signal, and like data that Simon still had, like shows that we're actually pretty close in terms of what we predict. Like, so we get like a molecular excitation blockade. Okay. So in the future, we want to look at higher dimensions, at lattices, and so on. And like Zoe also mentioned, maybe look at cavity effects, which I think are very interesting for these macrodimer systems. Okay, I'm out of time, and I'll just leave you with the conclusions here to read, and thanks for your attention.
Thank you, Valentin, for your talk. Any questions? Yeah.
So in your talk, you never mentioned a specific atom or a quantum number, a Rydberg quantum number.
Right.
Just calibrate me a little bit on.
Yeah. So this is rubidium, and the quantum number in the first experiments was 35. Now it's 36 for like reasons of specific reasons, but that's the ballpark.
Okay, and again, it's 1 Rydberg and 1 neutral?
It's 2 Rydbergs.
Two
Two
Rydbergs.
Rydbergs in the same quantum number, both 35. So you
Okay,
really
so
have this picture in mind of 2 Rydbergs down here separated by about a micron, and they bind via very weak polarization forces.
And when you say 1 quantum number for rubidium, I mean, there's a lot of different angular momentum states of the Rydberg electron on an isolated atom.
Right.
When you bring them together, are you considering just one N and L, or?
No, we diagonalized the full problem. I just flashed that slide, unfortunately, in the. So this is adiabatically connects to a 35p state here. But of course, there's significant mixture. So like the dominant states for the first experiments, well, are the 35p 1/2, 35p 1/2, and the 35p 1/2, 3/2 states. And then later that was changed, like going 1 principal quantum number up.
Fantastic. And so what goes into these descriptions of the individual atoms, there's a lot of multi-channel quantum defect theory that describes how all of the other electrons on the atom influence the Rydberg. And when you form a molecule, you get vibrational and rotational interactions that are on this roughly same time scale as the Rydberg motion. Have you thought about any kind of MQDT type description of the eigenstates that you form of those two electrons, and those two electrons themselves are coupled, so you have a
Right.
configuration interaction with those two electrons.
Right. So the single particle wave functions that are the basis of these calculations are, incorporate the quantum defect theory at short distances, but because the Rydbergs are formed at such large distances, actually, the single electron theory is pretty effective for these calculations, and you can see actually that the predictions, like if you include a large enough basis set, match the match the measurements within the kilohertz range.
It's a rich problem.
Yeah.
More questions? So you mentioned scattering results of microdimers that you skip, slides that you skip.
Right.
Could you just say just a quick word on it?
Sure. So here, the results that I showed you are obtained from exact diagonalization, really like just discretizing the continuum and diagonalizing, but you can obtain a similar picture by considering this as a scattering, like basically as a Feshbach scattering problem, where the open channel is the singly excited state, like you have a ground state atom and a Rydberg atom. They're unbound, so they live on this flat potential energy surface, and they're laser coupled now to the macrodimer channels, the ones that we just saw, with the vibrational states. And if you do that, that gives you like this kind of scattering potential, and through the phase shift, you can more directly see the lifetime, for example, of the state.
Okay. Okay, so let's thank Valentin and all the speakers of the session again.